Okay. All right. Now, what happens? sp2, lots of changes here. Geometry changes, it becomes sp3, and then this has the negative charge. So you have to attach something to that, and H perhaps proton transfer to neutralize the charge on the oxygen. Does that make sense? So at least we are seeing here the nucleophilic attack. But what does that do to the carbonyl group? Why is it addition? Because the carbonyl is double bonded. And then you will see the nucleophile, he sticks his nose in, right? He wants to be part of the group. And look at it. This guy becomes a single bond. So this is called an addition reaction. You're adding across the double bond. It's not a carbon-carbon double bond, it's a carbon-oxygen double bond. You see, the nucleophile comes in and the double bond opens up. Now, next we are going to compare. Of course, these are twins, aldehydes and ketones, not identical. So we have always to say, what does this guy do differently from the other guy? Now, we'll see why by the time we get to the end of the slide. These guys are generally more reactive. Okay, more reactive towards nucleophiles than ketones. Two reasons, as always, right? Steric and electronic. Now, of course, an aldehyde should have a hydrogen on one side, right? And for nucleophilic addition, this guy, he can sneak in from that end. But if you have a ketone, your R groups can be large R groups. So the nucleophile coming in is hindered to some extent. Okay. So if it's an aldehyde, only because he has a hydrogen on one side and an R group on the other side, it's easy for the nucleophile to come in and attack. And also depends on the sizes of the R groups that the ketone has. Electronic, okay? So now, if you remember, the CH3 group is electron donating. Think about the tertiary carbocation as opposed to the secondary carbocation. The R groups are electron donating. We know that too from the last chapter. So if it has a delta plus here, and I'm going to give delta means it's partial, right? Partial charge. So I'm going to make a fraction out of it. It's a charge, right? I'm going to make this 0.5. Okay. Initially, it's just explaining the fact. Then when these R groups are added, these R groups are going to donate electrons to the carbon. So this 0.5, because of this donation, right, our food bank is getting filled in with electron density. This could reduce to 0.25. You see that? It reduces to 0.25. After the R groups, start the donation. Now let's look at the aldehyde. This guy also, let's say, has plus 0.5 charge. Okay, that's what the delta means. It's a fraction. It's not a whole number. Now it has only one R group. Okay, so food from only one group of people. So this reduces to, say, 0.40. Okay, donation from one end only. So it reduces to only 0.40. Now think about this. The same nucleophile is coming from both sides. Let's say this is a nitrogen, okay, nucleophile. Let's not worry about what the actual structure of that nitrogen nucleophile is. It's coming in. Tell me which carbon will the nucleophile prefer? Tell me which carbon the nucleophile will prefer. Will it prefer the aldehyde's carbon or the ketone's carbon? Answers on the chat. Aldehyde. Okay. Everybody? All right. I want everybody to answer. I'm checking attendance. Shelby. Who else is there? Could one of you alert Shelby, please? And let her know attendance is required.
Why is she saying that?
Okay. So nitrogen here, this is negatively charged. So he is going to go on to something that is more positively charged. So, oh, she did. Sorry, Shelby. She was the second one to answer. I'm going to apologize. All right. So N minus will prefer the aldehyde. So we've established that aldehyde generally speaking, okay? Now, some nucleophiles require, here we are going to look at the pH, okay? What kind of a pH is required? Some nucleophiles require acidic. Of course, when it comes to pH, it's either acidic or basic. Now, we are going to look at, well, I think it's coming up pretty soon. We look at carbon nucleophiles, nitrogen nucleophiles, oxygen nucleophiles, okay? So if you're doing a Grignard reaction, this is basic. Conditions. Okay, we'll see what that means. So do you remember this reaction? And what is the product? This is the Grignard, remember? Me. Okay, I'm doing a rough sketch here, so you'll remember. Ultimately with the water. Now we did not know at that time that this is nucleophilic addition, but this is a good example of nucleophilic addition. This is the nucleophile, and we are converting a double bond to a single bond. Generally, a strong nucleophile means the reaction is under basic conditions. Okay. Now, if you put an acid in here, or if you lower the pH, these nucleophiles will not function. Under acidic conditions. All right. Just saying the same thing in a different way. Under basic conditions, all of the nucleophiles, it's just a generic mechanism. Okay, it's a generic mechanism. So we'll see a reaction under basic conditions, and then we'll see one under acidic conditions. So can we complete the mechanism? Let's practice. Okay. And also, if it is a strong nucleophile, under basic conditions, nucleophile attack will be the first step. Okay. When you have a strong nucleophile and basic conditions. I have to switch pens, I think. And then the next step you all know is proton transfer. Okay. I had to adjust my camera. Okay. All right, so the opposite of that, you see here, nucleophilic addition under acidic conditions. And when this is the case, proton transfer is always the first step. Okay. Proton transfer is the first step. So can you start off the reaction, please? Use that for the hydrogen. All right. So this is still nucleophilic attack. Next, the nucleophile comes in. Okay, because oxygen doesn't like the negative charge. I'm sorry about the pen. I ran out of ink on the other one. I believe this is better. The red ink is not good, right? I'll buy some good pens later. Okay, so the same product is obtained, but it's just a different route. Make sure it's still recording. Yeah. Always keep that in mind. Now they are probing a little bit more into the first step. Sorry. Carbonyl. Okay. They're breaking this down because we didn't really talk about something there. What can happen when you have a structure like that? Okay. What can happen when you have a structure like that? What's possible? Resonance, right? Yes. Shelby says resonance. Thank you. So then how can you draw the resonance structure? All right. So now look at this. You have a whole positive charge. Oh my gosh, I don't get this ink. Is this better? It's about the same, right? No. So you have a full positive charge, but it's a resonance structure, so it's not going to have the full positive charge the whole time, but definitely makes it a better an electrophile. Okay. So always remember acidic conditions, Always keep this in mind for nucleophilic addition and even otherwise too. If you have acidic conditions, PT first. If you have a strong nucleophile, nucleophilic attack first. Okay. So this will start off the mechanism fine. Okay. Once we have the groundwork down, then, you know, the mechanisms after that, they flow a little bit easily. Okay. So when a nucleophile attacks the carbonyl group, the equilibrium depends on the ability of the nucleophile to function as a leaving group. Okay, so what that is a nucleophile is coming in, right? And we want to lock him down. But if he's a good leaving group, then he's like, okay, I'm in, and then he'll go out, okay, just as fast. So for this reaction, what is your nucleophile? Cl minus is your nucleophile. Can you predict the product? Let's see. I don't want the mechanism, although you can write it down. Let's see if you can predict the product. Okay, Cl minus, that's your nucleophile. So we're only looking at what the product will be at the other end. We get something like this. Now, if you remember Cl minus, yeah, he's a nucleophile, all right, but this guy is a good leaving group. So what about the equilibrium? I would draw the arrow, the double arrow like this. You see that? So some nucleophiles are not good nucleophiles. Okay, they'll be in and then they'll be out. So you may have 75% of the reactants at the end and have only 25% of the product. Okay, so that's a drawback. So we've looked at what happens, what's the first step under acidic conditions, what's the first step under basic conditions, and then also is your nucleophile a good leaving group? Okay, if yes, then you're not going to get good products. All right, so keep those three in mind. Now these are the lovely nucleophiles that we will be looking at. But remember, the basic mechanism is the same. If it's a strong nucleophile, nucleophilic attack first. If it's a weak nucleophile, like look at these are all, some of these are weak because it's neutral. And then you will need an acid to start off the reaction, and then proton transfer is the first step. Okay. Now, you have looked at this before. What is that guy? If I put an Li plus here, and Na plus here. Do you recognize them? That's LaH. This is NaBH4. What are they? They are reducing agents. And if you go back to those chapters, you've seen those mechanisms before. So it's not new. And we've seen this quite a bit. We just saw it a few minutes back. All right. Okay. So we will be studying these as, I think the next one, which I'm going to start now, this is the oxygen nucleophiles. And then I think we look at the nitrogen nucleophiles and so on. Okay. It's 12:51, so I'll go for a few more minutes. Oxygen nucleophile. Look under the group that had oxygen nucleophiles. Okay, so we'll, Jaime, yes, want to type? Okay. So the first step, while she types, this is section 19.5, okay? We can see, yeah. Can you see now? Okay. Yeah, I don't know. I think because I moved it and, okay, good. Okay, so we're going to look at this. And then if we do this, these guys are similar. You see that? So it's not, it shouldn't be overwhelming, hopefully. Now, so water, okay, it's under the oxygen nucleophilic group. What's the product? This guy is used as a nucleophile as well as for proton transfer. Okay. So I'm going to predict the final product. I think it's my pen because I'm stressing on paper. It's a ball pen. Guess I'm going to the store today. I'm sorry about that. This is called a hydrate. Okay, this guy's working. It's called a hydrate. Now, this is, remember, what kind of a nucleophile is it? A weak nucleophile. Remember? So you cannot just add water to the carbonyl compound unless you have a very reactive aldehyde. All right. So it becomes obvious that we have to change the pH of the solution. Now we're going to see what happens under acidic conditions and then under basic conditions. Because it's water, you can go either way. So first we're going to look at the base catalyzed hydration. I think, let me look at the next slide. Yes. So what's the first step? Base conditions. First step is add the nucleophile. Okay. So this is the overall reaction here. You're going to have OH minus S the one that's providing the basic conditions. And then that's your water, okay? Which you will need later for proton transfer. So can we follow along? Okay. Now, because we are using water, you know, OH minus can be the nucleophile that produces the group that you need. And then what would you use? Why do they say base catalyzed? Because you get the OH minus ion at the end. Okay, OH minus ion at the end. So it is a catalyst. Be methodical in your learning, then it usually goes well. Now look at the next slide. Maybe you don't have the slides with you, so we're going to try the same mechanism under acidic conditions. So let me know what happens under acidic conditions. What will be the first one to attack? So you need an acid, okay? With water, you needed a base, so you had OH minus. For this, you need an acid. And look at which part of the carbonyl is attacked. It's the oxygen of the carbonyl that is attacked, okay? These are simple things to keep in mind, and it's very, very useful when it comes to writing mechanisms. When you do the nucleophilic attack, the carbon is attacked. When you have a proton transfer first, then the oxygen is attacked. All right? Okay, can you predict the product? And then you'll bring in your nucleophile. Show me what happens. Don't worry about the equilibrium arrows. Keep drawing them as regular equilibrium arrows. Will there be another step after that? Will there be a step after that? I would think so, right? Why? Because your oxygen is protonated. Remember the oxonium ion. So do you need another step? Proton transfer. Okay, and oh, how does this happen? I forgot to show that. and your H3O plus is regenerated. Again, acid acts as a catalyst. Acid acts as a catalyst. That's why it's regenerated. This is the H here. Next time I'll draw it bigger because we have mechanisms that are going to be long. Now, I'm going to continue and finish this recording, but it's 1 o'clock. So if any of you need to leave for any reason, I'll be fine. Just remember that we'll be meeting again on Friday and continue with this and start preparing for your quiz for next week. And then I want to have some practice problems for the rest of, for the end of chapter 18, so you have more practice. And I know you finished a sapling over that already, so that's what I'll do. Okay, so I'm going to continue. So I'm on a roll here, and is that okay that I continue recording for some of you? Quiz will be 18.8. Yeah, it'll be 18.7. I want to include that part as well because they all go together. So Shelby has a question. She's like, is it 18 point to the end? Okay, the end where we stopped. I don't know if we went all the way to the end. I have the book here. Let me check. Yeah, to the end. But no mechanism required for elimination addition reactions. All right, so is it okay that I continue, or would you like me to start on Friday? If I start on Friday, then we are just going to be slow and catching up. This way, I'll finish the section and y'all can watch the recording, whenever you want to. But I'll continue, right? Or any thoughts? The quiz for sure is what I'm planning to. We'll confirm on Friday. Okay, that's what I plan to. It depends on how we are going to do Tuesday and things like that. Okay, but tentatively Wednesday. All right. Till okay. Or I'll just do a few more pages. Okay. Doesn't go. So under acidic conditions, a mechanism will be reasonable if it avoids the use of or formation of strong bases. And this must be kept in mind. Okay, because in the mechanisms you'll see that I would say acidic conditions, and then you'll have something that is negatively charged, and that cannot happen, cannot exist under acidic conditions. Because if it's acidic, then the pH is going to be strong, and a strong base, especially if you have less of it, is not going to exist. Now, the opposite is true. You cannot have something protonated if I say that the pH is greater than 7. And we'll see, I'm just going to list that for now, but we'll see. What examples? Okay, when we look at examples, we'll see what happens there. But that's very, very important. Now we're going to use another nucleophile. We are going to use ROH. Okay, ROH. And you're using 2 molecules. This is under acidic conditions. RO minus is your nucleophile. Now this, when you have 2 OR groups, this is called an acetyl. You will see this in biochemistry. Glucose structures, okay, they can form acetyls or any carbohydrate structure. Under acidic conditions, again, you have to be specific. Is that acidic? Is that basic? One ketone molecule or one aldehyde will react with 2 alcohols. Okay, will react with 2 alcohols to form an acetyl. What are your acid catalysts? Sulfuric acid, I'm going to draw the Lewis structure to remind you what that is. And then para-toluene sulfonic acid. Remember your OTS? So we're going to draw the structure of that, well, the whole acid. Toluene sulfonic acid. Now it makes more sense to you, hopefully, right? Para-toluene. The sulfonic acid group. Orange. You see the similarity here? This part is the same for both. OTS is everything but that H is OTS. You'll not be drawing the whole structure every time. Let's look at the mechanism for the formation of the acetyl. It's a long drawn one, so you may need extra sheets of paper. Got that? Oxygen nucleophile. What's the first step? Okay, A minus, don't forget that. Okay. He already has a positive sign, so he's going to become neutral, the way they've shown it. Now, next, you're going to bring in your alcohol. Proton transfer. Okay. Now we'll make half the acetyl and then the full acetyl. I didn't show the arrows. Okay, so this is nucleophilic attack. What should the next step be? Proton transfer. So use another HA. So their acid, they've given this structure. Okay, given this structure. I'm going to use another molecule of water. No, I'm sorry. I'm just going to use another molecule of water. Okay. Okay. Now, if you look at this, and if you look at the structure that we need to get to, okay, this is the one we need to get to. Okay, so we are halfway. So what do they call this? Hemiacetal. Okay, hemiacetal. All right. So what have we seen so far? Proton transfer, because it's under acidic conditions, and this is the normal step. And they're using this as their acid. I'm going to use this as the acid. That's what you're used to, okay? All right. So then your A here will be simply water. Okay. Now, we've done half the mechanism, and I want to leave it at that. So it's not a whole lot more than where we stopped at 1 p.m. So you can go back and get to your homework and other things, of course. Okay. So I will anyway stop here and post this. Give me a second.